Hi everyone, welcome to our event. This event is brought to you by Data Talks Club, which is a community of people who love data. And we have a lot of events in our schedule. So if you're interested in seeing what we have in our pipeline, go check the description. So there is a link to all the events. Check it out. If you haven't subscribed to our YouTube channel, do it now. You will not miss out on any of the future events like this one. So don't forget to do this. And we have an amazing Slack community where you can hang out with other data enthusiasts. During today's presentation, you can ask any question you want. So there is a pinned link in the live chat. So click on this link, ask your question, and we will be covering these questions at the end of the presentation. And with that, I will stop sharing my screen. And Sean, the floor is yours. Yeah, and welcome, Sean.
Yeah, thanks for having me here. Let me do this exercise of screen sharing again. Thanks for teaching me this trick of sharing partial screen. Particularly helpful for me because I have a non-standard screen resolution. I enjoy it, but the sharing screen is kind of pain. Anyways, thanks, Alexi. Today, I'm going to talk to you about building an ML service platform from the ground up. So I think you can all agree with me that an ML model has not realized its value until it is deployed and served in production. But building an ML service for serving that model is more challenging compared to building a traditional service due to the added complexity of the model and data on top of just the service code. So what are these complexities? What are these challenges? And how do we work around them? My name is Sheng. I support the engineering team at BentoML. Prior to joining BentoML, I led engineering teams at the service infrastructure team at LinkedIn. We built back at LinkedIn the service framework that power all the distributed services for LinkedIn front and back end mid-tiers. Our goal for building a framework was to help developers and provide the right level abstraction of the infrastructure, though the developer of the application teams can focus on just the business logic that matter to them. And it's also from there that I learned the value of a good framework can deliver to engineering teams and how it can help them to focus their energy on things that truly matter to them without having to worry about the infrastructure. And this is the role that I see BentoML plays. And when I discovered a project in open source, I was quite excited to find a project like this. And I was really impressed by its vision. I like to see finally that a project in open source can deliver value to not just teams in the same company, but a vast community serving ML models. So my journey joining BentoML is a little bit unconventional. I started working on the open source side with the team for about a year, longer than a year, until I joined full time. Reflecting on it, I think this is a rewarding process because I truly get to learn about the project, about the team before I commit, and also gives a very good lengthy two-way interview process. So for both the team to learn about me and for me to learn about the project and the team. I do recommend this if you considering joining an open source company. Maybe not for a year, but definitely work with the team to test out what it feels like. So BentoML is an open source framework that we created for serving ML models and deploying ML models. It has been adopted by hundreds of organizations around the world across different industries. So today I'm going to talk to you about the considerations and learnings that went into building BentoML. So what's the problem that we're talking about here? As a data scientist, once I've trained a model and I'm pretty happy about a model's performance, how do I get it out to the world so everyone can consume the model that I've created and truly to deliver the value of the model to the end-to-end applications? The most common way is to put it behind the API endpoint. So you call post hot dog or not, and it returns a result to you through HTTP. What solutions are out there? What solutions are out there for serving? So today, I'm going to evaluate the solutions across two dimensions, the ease of use dimension and flexibility. And why ease of use is important is this will allow you to quickly deliver value of the model, have a very quick time production, and also doesn't require very complex skill sets for engineering, infrastructure, and DevOps. Flexibility is important because it allows the solution to grow and scale with your team. Because as you onboard more use cases, as your team grows, the solution can grow with you. So it can expand to the complexity of your team growth and use case growth. The first group, what I call the off-the-shelf solutions, they are there are many off-the-shelf solutions out there, depending on the kind of the framework that you choose to train your model in. If the model was trained in TensorFlow, you may consider using TensorFlow serving, or if the model is trained in PyTorch, you can consider using TorchServe. There are more generic frameworks like the Triton Inference Server, which support multiple different ML frameworks. They call it backends, such as Onyx, TensorFlow, and TorchScript. To use these frameworks is relatively simple. You only need to provide the model with, you only need to provide the model that you want to serve, along with the set of configurations that describing how you like to serve the model. And these frameworks usually come with a pre-built server, the server binary, or the Docker image out of the box. So you can just use the provided image. Given the three tuple, the model, YAML is the configuration, and the image, you can very quickly get a model server for your use case. And the input and output are usually tensors for the most common machine learning use cases. And these frameworks are typically great for low latency serving because they run their models on a very specialized runtime that's highly optimized for performance. Because it's highly optimized, they can usually utilize the underlying hardware quite well. However, these problems comes with some limitations. First, the definition of how your business logic, how you like to run your model is quite limited. So they're written in different languages, right? They're languages and frameworks. If you train your model in multiple of these frameworks, you kind of have to choose and learn all the different solutions. So if your model is in both TensorFlow and PyTorch, you may have to use both TorchServe and TensorFlow solutions for model serving. And these model inference rules are defined in a declarative way through configuration YAMLs. YAMLs are simple, but they complicate the development. Not only the user has to have to learn all the different meanings behind the settings of the YAML, and they cannot iterate and test these YAMLs quite easily. So every time you have to restart the image, providing a different YAML, it's lengthy, it creates complication during development, and it doesn't provide a lot of good visibility into what's going on inside the image or the server. Second, the inference is really just model inference is really a small part of an ML service. These solutions do not offer a good way for defining custom logics like pre and post processing, data validation, feature transformation, and the input and output types are not limited to just tensor, right? Common use cases also include tabular forms like pandas data frames, or JSON, or files in the form of audio, video, images. These are also very common input and output types for machine learning use cases. Lastly, many of these use cases require not just a single model inference, but requires multiple models to work together, either in a sequential way or in parallel. Multi-model inference is what we call it. Multi-model inference is when you have an ensemble of models working together, again, either in a sequential way or in parallel, together to form an inference result. So in this example that we see on the screen is a credit application example where we first take the input and run it behind the fraud detection model to determine whether the application is genuine. And only if we determine that it's not a fraud do we fan out it to 3 different risk assessment models. And the inference of these 3 risk assessment models in parallel. So once we get the results back, we post-process it and form an output. Sorry. So the challenge of using the off-the-shelf solution using this is that we may have to, first of all, it may not be supported, this kind of multi-model inference very well. But for example, like Triton Inference Server do support model ensembling, but it runs into another problem is that you're forcing the coupling of these models into the same runtime. But these models and the business logic may not be most optimal to run and scale in the same runtime because some may be best run on a GPU environment, some may be best run in a CPU environment. You'll end up having to allocate an environment that runs both GPU and CPU. It can get really expensive and it gets really inflexible. The ideal way is that you can scale them independently on the hardware environment that's best for running them. So in conclusion, for the ease of use group of applications, group of frameworks, they're pretty good for low latency serving. And they have relatively low development cost for simple use cases. But the challenges come in when you have multiple of them working together. Frameworks, because they're framework specific and configuration driven, they're quite inflexible for customizing inference logic. Lastly, they have limited multi-model inference and scaling options. So the second group is what I call the in-house solutions. This group consists of generic frameworks like FastAPI, gRPC, and the Golang that help build your ML service from scratch. You can define your custom business logic quite freely because these, at the end of the day, are very generic frameworks that you can practically build anything. So the first, the most natural way to build a solution like this is to put the models in the same server runtime. So you can freely define any control flow, multi-model inference in the same server because you have full control of the server again. The challenge with this approach is that, again, you're co-deploying the models and the business logic in the same environment together, similar to what we saw previously with Triton Inference Server. It gets inflexible because the models may want to run in different environment and hardware profiles together with the business logic, right? So not only do you have the more compute-intensive workloads like the models, the business logic is typically maybe more I/O intensive when it gets to feature transformation, looking up embeddings, loading data from another source. Again, it gets more inflexible because you're deploying these logic in the same environment. And now that scaling option is quite limited because you can only scale the server itself, but not individual components inside the server. Alternatively, we can deploy the models and the business logic as different distributed services, allow them to run on their most optimal hardware, and at the same time, they can scale it very independently. With this type of architecture, you can also define any control flow, multi-model inference quite freely because you control the the invocation of the model inference calls, kind of as RPCs. However, but using this form of serving is hard to develop. You now have to solve all the problems that microservices bring in, such as API compatibility, RPC, service discovery, load balancing, and all the problems that distributed services see that you will not have to solve. And regardless of which service architecture that you choose, to build and deploy end-to-end, you still need to work with Docker for containerization and Kubernetes for deployment. The challenge of using this framework is that building ML service from scratch is, again, very hard and expensive. The skill set that's required here, it does not align with data science teams very well. While this solution is flexible, this group has very high engineering cost and time to market, which makes it quite unaffordable to a lot of the smaller data science teams. So the in-house solution, we think is more flexible, but it's not very easy to use because we're building pretty much from scratch using the microservice development frameworks. It's quite flexible, so it practically allows us to build anything, including custom business logic and multimodal inference graph. The downside of using this approach is that it has high engineering costs and time to market, and it has skill set mismatch with data science teams. So having discussed those two previous quadrants, let's explore what an ideal solution looks like that's both easy to use and flexible. So let's look at what the dream quadrant would look like. First, the solution should be flexible for defining custom logic and multimodal inference graph. Instead of declaring the business logic using configurations like YAML, we want to do so imperatively, maybe use Python. Declarative programming, you already know this, is a paradigm where you describe what the program does, where imperative programming is a paradigm that describes how the program does it by giving it step-by-step instructions. Imperative programming is more natural when it comes to defining the very flexible business logic that we think. On top of that, the intention of YAML is to simplify business logic definition without asking user to really learn another programming language. But think about this, we see a lot of frameworks when we see YAMLs, it kind of get intimidating. We have to learn the meanings and details behind it. So YAML often fails to do so, to simplify defining the logic. On the other hand, we already have this language, Python, that's already very common programming skill among most of the data scientists user groups. So it also has great community support for ML libraries. So instead of defining the inference logic declaratively using YAML, we think the better solution is to do so imperatively with Python. Second, we want the different workloads to run on the most optimal runtime and hardware profiles. So this time, not only do we have the compute-intensive models that's best run on GPU or multi-core CPUs, we also have the potentially IO-intensive logic, such as pre-processing, feature transformation, accessing information from a database or an external API. So on top of that, these workloads should be able to scale independently from each other without having to statically define the number of replicas to run in a container. More so, these workloads should be scaled automatically to best utilize the resources that you have. Third, we want the deployment to be in the form of the most optimal for the environment that's running the use cases. For example, a simple proof of concept use case we may want to just deploy as a single container in a serverless environment, where for teams that manage their own clusters, the same service should be able to be deployed on a Kubernetes environment. Other deployment targets includes batch inference tasks on Spark or streaming inference on Kafka or Flink. Users at the end of the day shouldn't have to rewrite their service just to deploy in a different environment. Last but not least, the solution, whatever solution that we come up in this quadrant should have low development cost that's provide the right abstraction of the underlying hardware and without exposing the complexity of the networking. So all of these considerations are what we went into building BentoML. BentoML is an open source framework for ML serving and development. Again, it offers a unified API that supports the most popular ML frameworks out of the box. The SDK we provide is a Python SDK, so for you to define any model inference or custom logic inference graphs. BentoML also standardizes the deployment process through the Bento artifacts, so allow user to build things once and deploy anywhere in the environment that's most suited for the workloads. So, and also since BentoML is Python first, it natively integrates with all the ecosystem tooling, such as Airflow, Kubeflow for pipeline, or the different model monitoring tools for observability. So by offering this capability in Python, these just come for free. So again, so we can have all the different ML frameworks using Python, writing Python API, and we can build a Bento once and deploy in any of the environments on any of the public cloud platforms. So what you see on the screen right now is the credit application service that we previously seen. So let's see the credit application service again. So to evaluate whether a credit application is approved, we first need to do a little bit of pre-processing to fetch the features and feed the feature and the input into the fraud detection. And only if the fraud detection deems that it's genuine do we pass it to the 3 risk assessment models simultaneously. And then at the end, we combine the responses of the 3 risk assessment models and post-process it to form a response. So let's take a look at the service step by step and understand how do you write a service like this in BentoML. So remember in the graph that we have 4 machine learning models. So we can model them behind this concept called runners in BentoML. Runner represents a unit of computation in BentoML, whether that's model serving or some custom business logic that can be scaled independently. So in this case, we use the BentoML API. Say the fraud detection model is a PyTorch model. So we can use the BentoML PyTorch to load the model and create a runner out of it. But the risk assessment models are sklearn, so you can use different frameworks together in the same framework. We load the model using sklearn and then turn them into runners. Runners also provides the capability for you to run batch inference. The batch inference is when you want to run a sequence of requests against inference on sequence of requests together. Is more optimal because it helps utilize the hardware vectorization it's more optimal compared to running each of the requests in sequence. So you want to batch as much requests as possible. But in a serving environment, batching is a little bit tricky because you don't really control the arrival rate of the request. So how the runner does that is that it waits for a configurable amount of time to batch out the requests that are coming in during that time. And it provides the inference of all the different requests that are coming in that batch. and distribute it back to the callers. So the callers don't feel like the request is being batched, but it's being batched transparently behind the scene. Once we define the runners, we create an application. In this case, we call it the credit application, and we pass the 4 runners we previously created to the service. The more interesting part is the API definition. So at the very top, we see that we created the input and output as JSONs. So JSON is one type of input and output that's supported by BentoML. Besides JSON, BentoML also supports input output such as tensors and tabular forms like pandas data frames, or files in the forms of video, audio, images are all common I/O types in BentoML. So, and this can be customized by you can write your own custom I/O types for the very specific use cases for your models. So once we have the JSON input, we pass it on to a feature store. So we fetch the features asynchronously using the user ID. Once we get the features, we pass both the features and input data to the fraud detection model. We run it asynchronously. With the result that we're getting back, we determine whether it's behind. Are we confident that it is genuine? We reject it immediately if it's not. We pass it on to the risk assessment models if we think it's genuine. So this type of control flow, conditional control flow, is supported in definition of multimodal inference quite naturally. In here, we use async IO to find out simultaneously all the requests to the 3 different risk assessment together with the feature that we previously fetched. And at the very end, we combined assessments into a single response back to the user. So the waterfall graph for this service definition will look like this, where we first do pre-processing and fraud detection. 3 risk assessment happen simultaneously around the same time, and then we post-process it to return a response. So to achieve this simultaneous computation of models, we do it through different forms of the deployment. The first, most common deployment is a container-based deployment, where all of these components are run inside a Docker container. So we have multiple copies of API server. This is to allow the inference to work around the Python GIL, the global interpreter lock. So we by default deploy the same number of API servers as the cores available to the container. Oops, sorry. And the models can either be deployed as a singleton or as multiple instances as well, depends on the best way to run that model. Some model frameworks supports multi-threading and the utilization of the GPU, so a single instance will be sufficient. Some model frameworks, or just basically custom logic runners, you want to duplicate for the same reason that you want to duplicate your API servers to work around the Python GIL. So you have ability to control and configure how you like to deploy your runners in the same container. Beside the container-based deployment, we also have Kubernetes-based deployment. For Kubernetes, we offer the Bento and Bento deployment CRD. For these type of CRDs, we're able to deploy the different workloads on different node groups as scalable pods. So for API server, again, is probably most optimal running on single core CPU. So we can scale and deploy API server on the single core CPU pods, where for the models we want to deploy on GPU and the multi-core CPU pods, we can run them on the different hardware profiles and scale them independently from the API servers. And this is possible through the custom resource definitions that we provide in the BentoML provides in Kubernetes development. Yeah, so in conclusion, we explored the two quadrants of the available solutions today. So, and we at the end we explored what an ideal solution should look like for model serving. So, in summary, they fall under three categories. So, first, the optimal solution should be able to customize your business logic, definition, and inference graph. It should provide optimized runtime for hardware scheduling, scheduling on different hardwares, and allow independent scalability. Lastly, it should support multiple different deployment environment, whether that's a single container or on Kubernetes, or for example, on Spark or Kafka, without user having to rewrite a single line of code. So yeah, I think that's it. Thank you. Thank you for your time. If you find the talk helpful, please check out our BentoML Slack community by scanning the QR code. And any questions?
Can you show us how to give you a star?
Go to this link and you can click that star.
Okay. Does it support AWS Kinesis? So you mentioned it supports Kafka. It supports like what kind of other streaming platforms does it support?
It's not as natively supported in Kinesis as well. It's not as natively supported at this point. But what you can do is
like Flink, right? Or
what you can do is deploy an BentoML service and host it in your Kubernetes environment. And what we provide is a Bento client that you can use in any environment. So you can spin up that Bento client in your Kinesis environment or Kafka or Flink and call the service that you deployed on the Kubernetes environment.
I've heard you also have some support for serverless, like for AWS Lambda. And Lambda is really well integrated with Kinesis. So like what I like about this using Lambda with Kinesis that you don't need to care about anything. So you basically just say, okay, connect Lambda to this Kinesis stream and then write some code for processing data from the stream, and that's your job is done, right? So that
yes,
you don't need to worry about anything. And I know with Bento, you can also deploy a Lambda function, right? So then will it be possible to connect this Lambda function to a Kinesis stream, or still not really?
Oh, you can definitely do that. So BentoML is the framework for developing your model serving, but we also have this project called the Bento CT.
You're
Bento
not sharing
CTL.
your entire screen, remember?
Yeah, let me adjust that. This is better. So we have this project called Bento CTL, and this project allows you to deploy the Bento you have developed into any environment, cloud platform environment possible. So, and the AWS Lambda is one of the supported environments. Mm-hmm. And again, in the Kinesis stream, you can use a BentoML client that we provide out of the box. So take a look at the client implementation. So you can very easily just provide a URL of the client. You can call the client in any in the most native way to your inference service.
Okay, so then it means that we deploy Bento in some way, and then from our Lambda we can just invoke Bento through this URL, right? Through the client.
Exactly.
Okay, got it. Okay, that's quite convenient. Then you also showed, like when we were talking about Kubernetes, and you said that there is CRD, that's custom resource definition, right? Can you maybe show us an example of how this, like an example of this YAML file that, for example, for this application that we talked about, do you have an example how it might look like?
I don't have an example for that exact application, but
Maybe it's for
what I can
something
show
else.
you is we have an uh, deployment platform called Yatai. This is the platform for BentoML deployment on Kubernetes. So this is an abstraction on top of the Kubernetes environment. So when we deploy a model, so the fields that you see in here are kind of like a visualization of the custom resource definition. So once you provide the cluster that you want to deploy this in, give it a name, and selected a bento that you want to deploy, you can sort of define the what's in the custom resource definitions are kind of what you already see on the screen. You said how many replicas do I want to deploy this in? What's the resource I want to allocate to these replicas? CPU, memory, or any custom resources like GPU. I can define both the API servers and the runners. So in this bento, I saw that I have a runner called PyTorch Minist. So the runners, I can also say, oh, I should be able to auto scale from 2 to 10 and give the resource definition for each runner and API server independently. So what you see here is a kind of like a visualization of the custom resource definition that you see in Kubernetes. So where in Kubernetes, the custom resource is defined in a YAML file, you can use kubectl to apply or update the deployment configuration for the resource. Here is a visualization of what it looks like on the user interface.
Well, what do you use for auto scaling? Like, do you use some specific metric? Is it CPU or request per seconds or what?
Yeah, it's a pretty much configurable.
It's
If you
configurable.
use
Okay.
yes, you can use CPU, memory, or any custom metrics. We're working on a native way for scaling GPU, so that is in the work. We're expecting that to be out very soon.
But by default, what do you use for scaling up? Is it
By default,
CPU?
is CPU and memory. Yes.
Okay. I think that's in Kubernetes in general. That's the default metric, right? CPU.
That's what we set here by default. Yes.
Okay. Yeah, and I'm now, to be honest, the reason some time ago, team did a demo in our open source spotlight, and in this demo, so team mentioned this batching. So you also talked about that, and I thought, okay, like this is really cool. But Tim, can you come to our webinar and tell us more about batching? So I'm wondering, how does it actually work? I'm really curious, how is it implemented inside? Maybe you can tell us a few words about like what kind of technologies do you use there? Like how does it actually, like what are the processes there? Like is it one process? Is it multiple processes? Like, yeah, maybe you can give us a glimpse into this architecture and implementation.
Sure. I'll try to dive a little bit into the details, but it's really no magic how it batches. The philosophy behind batching is that running requests in batch is more efficient and turn out to be in aggregate faster than running each individual request independently. And wherever possible, we want to run batch inference to the model. And batch is more natural when you do offline inference. The challenge comes to when you do online inference, how do you dynamically batch it together? Because arrival of the requests are kind of out of your control. So what we can do in theory is have a configurable amount of time that you're willing to wait for a batch to form. And this configurable amount of time should line up very well with your SLO, service level objectives. So this is the maximum amount of time I want to wait, because beyond that time, the response is probably not as meaningful to me anymore. The user waiting for the response, lose their patience, or the depends on the use case. So this is again, it falls back to what your service level objective is. So once you provide that value, and together with another configuration called batch size. So batch size is what's the maximum amount that you want to batch in the same group. Batch size matters when sometimes when model you don't want the batch size to be too big, so it consumes all the resources available in your system. You want the batch size to be just optimal so that you run an inference before you run out of resources. The combination of these two parameters is fed into the batching algorithm, and the batching algorithms will is a regression model itself. So they try to figure out what's the most optimal batch size with the most optimal latency for running the batch.
Okay, so you're doing some sort of online learning, right? So you're recording some data, and then you see, okay, like for this batch of for this size of a batch, it took this time. For this size of a batch, it took this time. Okay, what's the optimal size, right? And you adjust this.
Exactly. So cool. The first few groups of batches are kind of like the tuning and the experimental. So it kind of converges to the most optimal size. But as your traffic pattern change, the dispatcher is capable of adapting to the change of your incoming traffic, again, to adjust the size and the amount of time that it waits to provide you the best possible batch.
That's interesting. And like, how do you actually implement it inside? Is it some sort of like a queue, or what is inside this dispatcher?
It is a queue. So basically, that you have a inbound and an outbound, right? So I can actually point you to the code.
Yeah, maybe if you can do this would be like, is it like a standard library, or you use some sort of like external library for all this concurrent stuff?
No, it's just standard libraries. So it's asynchronous, basically, processing. I think it's under here. Oh, we recently had a. So all the code for batching is really in this dispatcher code. So we have an optimizer, again, telling you this is regression model that we try to figure out this maybe this basically AX plus B, right? What's the most optimal A and B? Like they try to learn this over time. And there's the Quark dispatcher. Basically, it takes a bunch of input on the inbound, and then wait for the most optimal amount of time, and then release the Quark, right? And then feed it to the model. So every time there's a request coming in, it invokes this call function, and then it batches and it accepts more requests. So once the most optimal time has come, it'll trigger another event to release the Quark. So this is the code. There's no magic. Check it out.
Yeah, I thought it would be larger. I remember from my Java days when I was a developer. So in Java, all these libraries for concurrency, they are much more, how to say, comprehensive. While in Python, it's not so much. But I see that you can do quite a lot actually with Python too, with this dequeue, right? So you use a dequeue there.
Yeah, Python has some syntactic sugar for handling async programming. Java, it gets a lot more verbose when you have to write using specific libraries. But here mostly is just most common libraries in Python.
Okay. Yeah, thank you. So I'd like to share my screen because there are a couple of questions that it will be probably easier for you if you just read it from my screen.
Yeah, certainly.
So a question from Adonis. In 5 years, do you think the required development skills of machine learning engineers will be different? Will it become simpler because of tools like BentoML?
Definitely. I think this is a great question. It also, sort of asks the philosophy for building framework and MLOps toolings like this. We think that in 5 years, developing ML is going to be much simpler than what it is today. I think we have seen this from the previous 5 years. If you ask this question from 5 years ago and evaluate now, it's definitely a lot simpler compared to what we had to do 5 years ago. And this is going to continue to get simpler. We think that maybe the most important skill for building ML models is the domain knowledge, as opposed to understanding the complexity of the model algorithms itself, or even data. Data is the biggest problem today. There are tools for cleaning data, understanding data, data comprehension. So I think that problem can get solved in 5 years. The process is going to be a lot simpler. Any domain expert will be able to train a model in their domain. The skill set required is probably just Python. Don't code on me, but I think it's going to be
Yeah.
Python is going to be that skill set.
I was going to ask you that because now if you look at the job descriptions for ML engineers, you need to know not only Python, you also need to know, like, I don't know, Kubernetes, CI/CD, like all these testing frameworks. You need to know, like, I don't know, Terraform. You need to know, like, a cloud or multiple clouds. And sometimes a lot more, right? So that there is quite a lot of requirements, especially from like more senior roles. Do you
Yeah, I
think
think
we
those
will not
are.
need this?
I think it'll get simpler. How far we'll get depends on the advancement of these tools. So we're working very
Mhm.
hard to simplify it. Um, it's the in reality the difficulties of finding engineers or data scientists or individual with these skill sets is harder, right? It's and also it's not core to building the machine learning model. Like, why do I have to learn Kubernetes to be a machine learning engineer? That just uh, unfathomable. But in
Mhm.
reality today, because you need to deploy your model end to end to
Mhm.
production, then you can only deliver the value. I think that's the theme overall talk. Um, then you have to have these skills, but these are not really core to completing your machine learning tasks, and they will get simpler. And tools like BentoML and there are other uh, tools in a similar domain are looking to solve this problem. So BentoML's vision is that you can write Python and write Python only and deploy the serving logic in a distributed way, in the most optimal way, and the deployment environment possible, right? If it's that's the deployment environment is Kubernetes, it will deploy in a distributed way as microservices behind different pods. You don't have to worry about it. Like, you can leverage the power of Kubernetes by just writing a Python program as if you're developing a very simple Python module. So the complexity is abstracted away from you.
But you still, like as a ML engineer, if I want to use Bento now and deploy something to Kubernetes, I still need to know like how to use kubectl and tools like that, right? So I need to know what is a pod, what is a deployment. Like I still need to know these things, or
No,
I
no, you
can
don't
get
have
it.
to.
I
So
don't have
that
to.
you can, like, there's, if you prefer to use kubectl to deploy, there's a capability of doing that. But if you want to get away from abstract all that away, remember the previous deployment platform that I showed on screen share. That's one way that you can deploy a machine learning models through just a panel, like console application, not console application, but the deployment platform that you have on the user interface by defining basic things like how you like to scale, how many, what resource you like to allocate. Uh, you can get away from having to learn the details of Kubernetes.
Hmm. But I still, I guess, have to have kubectl installed and configured. Otherwise, Bento will not be able to communicate with Kubernetes cluster.
Only has to installed on uh, the machine that runs the deployment platform. So
Right. You
you are
showed
using
this
it
UI,
through.
right? So on that
Yes,
UI,
yes.
it has to be configured. And if I'm a data scientist, I just want to deploy my model to Kubernetes. I will go to this UI, right? and then use it to
Yes,
deploy my model. So
absolutely.
I will not need to download kubectl, configure it to run on my machine.
Correct.
Okay, cool. So who's your target user then? Like, is it a machine learning engineer or a data scientist or both?
We're both. So I think there are different levels of abstractions of the product to different user groups. For data scientists, it's more has a Python interface, and you can build and deploy your model through the user interface environment. Where for machine learning engineers or ops, if you're more familiar with the Kubernetes environment, you can directly using kubectl. So there are different abstractions for different personas.
Okay. Okay, I guess we covered that question in a lot of detail. So why API server in single core CPU? Could you please share more details? I don't know if you need to
Yes.
share your screen for that. Should I
No,
stop
that's
sharing?
okay. I think first of all, that was an example to demonstrate that you are capable of deploying the different workflows on different uh, types of pods. You don't have to, but why is it most optimal to run on single core? Because API servers are more uh, is limited by Python GIL, so you can run only one of it. Like uh, there's no parallelism running Python runtime. But if you deploy a multi-core CPU, BentoML is capable of deploying multiple instances of your API server. So it best utilize the multi-core CPU that you have provided to it. It's just an example to demonstrate that you can independently deploy and scale them, not necessarily that you have to deploy them in a single core CPU.
Do you know if Python is going to get rid of GIL anytime soon? Not really, right?
I heard of this coming, but
Yeah, I
I
feel
don't
like I
see. I don't.
saw this topic popping up in Twitter threads, but it's not happening,
I
is
guess
it?
until it happens.
Yeah. Okay. But with I think IO, it became a bit more manageable, right?
Um, it doesn't. It's independent of GIL,
Mm,
so it allows you to write asynchronous programs easily, but no, there's still no
mhm.
parallelism.
Yeah, right. Okay, so what's the difference between kubeflow and BentoML? And here, I guess by kubeflow, the question means the is kubeflow serving or kserve.
Yeah, so Kubeflow is a large ecosystem. So inside of it, like Kubeflow has notebook support and has pipeline support. And in its deployment solutions, it has Kserve. So BentoML is more comparable to the deployment part of the Kubeflow ecosystem, so to Kserve. But without getting into a lot of details, the deployment philosophy is actually quite different. Kserve has its sort of model mesh deployment philosophy where multiple models can be deployed in the same environment. It's abstracted away uh, uh, using Kubernetes constructs. But now does not get into that model mesh domain where it more directly interface with Kubernetes. So I don't think this explanation do the justice that's needed to the difference between Kserve and BentoML, but do a little bit of research. It's quite interesting what Kserve does. It has a lot of benefit as well. For example, the scale to zero capability, so it's quite cool. But Kubeflow, again, to answer this question, is a larger ecosystem that it's more end to end. People user use it for developing on notebook pipelining and deployment. And BentoML is more focused on the deployment and serving part. We are working with Kubeflow on providing an integration, so Kubeflow users can more easily deploy to BentoML.
And when it comes to kserve, it's mostly YAML. So you configure all the you configure the location of your model in YAML, so you don't really have Python. And in fact, I think it's written in Go.
Correct.
So you're not supposed to see Go code you only do it through YAML through custom resource definitions in Kubernetes, and that's all you have, right? So there is no. So on one hand, maybe it's convenient, but on the other hand, maybe you have less flexibility because of that, right? Because with BentoML, you can do everything you want because you have Python, right? But when with Kserve, at least that was my experience. Like you're a little bit, like you have less flexibility. Then you have to include all this custom logic in pre-processors or post-processors, and then like think
and
exactly
stitching
how.
multiple models together.
Exactly.
Thanks,
But
Alex.
that's it's a very nice framework indeed. Check it out. Okay, the last one. So where do you usually store and how you serve semi-structured data that varies in schema, likeness to JSON?
I'm not quite understanding this question, so I'm gonna try to rephrase it. Maybe Alex, you can help me here.
Yeah, let's try.
Understanding the question. So where do I store the unstructured? So BentoML is an online serving, so it doesn't keep the state or store the inference data, like the input and output data. It's up to the caller of BentoML, and it can be coming from a user directly, or it can come from a stream. There is no limitation to how you where the data come from or how you store the data. BentoML is more of a inference framework, so as opposed to storage. Alexi, did I understand this correctly?
Yeah, I'm not sure. So the way I understood this question is like if we have a model that is supposed to somehow answer requests that are different in schema. So one time you get JSON that looks like that, and then the next time you get JSON that looks differently. That's my interpretation. But I'm not really sure, to be honest. It depends on the model that you use at the end, right? So if a model can handle all this, And with Bento, because at the end it's just Python, right? So you get a dictionary. In the example you showed, it's just a dictionary with input. Then you can do whatever you want to do with this input and prepare it in any way you want in order to put it inside the model.
You get the unstructured data, or you get a nested JSON, and then it's up to your inference logic to decide what you like to do about this JSON. And optionally, you can define a schema for this JSON as well using something like Pydantic. So it provides you the validation, gets you a strongly typed object that you can work with.
Mm-hmm.
So, if you like to dive a little bit deeper with that question and that didn't understand it fully, find me in the BentoML community. I like to help you or explore a little bit more around this topic.
So you'll give us a link, right? I think I saw in GitHub when you showed some code in GitHub, there is a link to BentoML community, right? So that's, I guess, the best way to find the community. Just go to GitHub and then find the link there.
Yeah, just Google it. I'm sure.
So maybe the last question. I see there are quite a few questions in live chat. We don't have a lot of time. I actually need to go now. So let's take one question. So how do we select batch dimensionality, which is 0 by default? Like, do you have any rule of thumb for that?
Yeah, so that's really how your model treats how you manage your input. But by default, the dimension, the batch dim is 0. You can change that to anything when you save your model. So when you what I didn't show in the presentation is that there's actually a training saving step. So when you're saving your model to be used in BentoML, you can provide the metadata to tell the model framework that, hey, my batch dimension is 0 or 1. You can do this independently for input and output. Your input and output have different batch dimensions. 0 is just the most common ones, and if you go to other frameworks, they sort of make this assumption by default. And I'll give you the flexibility. Sometimes your batch dimension is different, but you can define that when you're saving your model.
Okay. So we haven't answered a few questions. As I understood correctly, the best way to reach out to you would be BentoML community, right?
That's correct.
Then LinkedIn.
Come check out our community there. Oh, sorry?
Yeah, I was going to ask, like, do you check LinkedIn if somebody writes you to LinkedIn? then
Yeah,
would it
I'm
be fine?
pretty active on LinkedIn as well. Find me on LinkedIn as well. Sheng is my name, so you should put that together with BentoML, can probably find me quite easily.
Sorry, I interrupted you. You wanted to say something?
No, no.
No? Okay, thanks a lot for coming today, for joining us today, for doing the presentation, for answering all our
Thanks for
questions.
having me here.
Yeah, that was like, I really admire companies that put all this effort in open source. So thanks for doing that.
Oh, thank you, thank you, thank you for all your support, and thank you for having me here. I really enjoyed the conversation, and have a good day, evening, afternoon, wherever
Yeah,
you are in the world.
yeah.